Good morning. The purpose of this lecture is to demonstrate how the analysis of time complexity values for T of n can be validated empirically. Example 1. Find and verify the time complexity of the code fragment in figure 1. So our code fragment is int sum equals 0 for int I equals 0, I less than n, I plus plus, sum plus plus. So solution, first find an expression for T of n. So we do our 3-column table with the line numbers in the left column, the statements in the middle column, and the cost in the right-hand column. And as we demonstrated in the previous lecture, we come with a T of n value equal to 3n plus 3. Next, we create a C++ function that computes T of n analytically. So we call this appropriately analytical. Int analytical takes a single parameter n and returns 3 times n plus 3. Next, we create a C++ function that computes T of n empirically. So what we do here is we call the function empirical. We give it the same parameter as analytical. And we introduce a counting variable c that is going to count the number of times each statement is executed. So we initialize it to be 0, and c is our instrumentation, if you will. And so when we assign 0 to sum, we increment c. When we assign 0 to I, we increment c. And we increment c every time the comparison is true, I less than n. We increment c every time sum is incremented, and we increment c every time I is incremented. And we increment c one more time when I is exactly equal to n on the closing curly brace, and then we return the value of c. Now what we do is we write a program that exercises both function and presents results. So I make a title that has n, analytical, and empirical as columns. And then I make another function that is row that prints one row for n, one row for analytical, and one row for empirical. Then I give an array of values for n, 0, 1, 10, 20, 30, 40, 50. I print the title, and then for a equals 0, a less than 7, the number of values for n, I print the row analytical, and I come out with an output that says when n is 0, the analytical function produces 3, and the empirical function produces 3. So in every case, for every value of n, what I'm able to determine is that the same value is produced for both the analytical and empirical, and I get a great sense of security and assurance by testing my analytical values against those that I computed empirically. In this technique, if we ever discover an error, the most likely error is in our analysis and not in our empirical record of what happens. So for example 2, find and verify the time complexity of the code fragment in figure 2. So here I have another loop, and what I'm doing here is I'm incrementing by 2 rather than by 1. So what I get is I get a T of n that's equal to 3 times the ceiling of n divided by 2 plus 3. So my analytical function is if n percent 2 k plus plus, return 3 times k plus plus, and I do k is equal to n divided by 2, and my empirical, I just have the code exactly with the instruments of c. So when I get ready to print it out, I have values of 0, which produces a value of 1, which is an odd number. I get values of 6, value of 10, which is even, a value of 11, which is odd. And for every value, it appears that I have been successful in making my analytical function match my empirical function. For example 3, find and verify the time complexity, and here I have of the code fragment in in this figure, and so I have a nested loop. So the I loop is going to execute probably n minus 1 times, and the J loop is going to execute B times, which is going to be probably some function of n squared. So when I get down here to my total, I've come up with the T of n is 4a plus 3b plus 3, where a is equal to 0 to n minus 1, or n, and b is equal to n squared. So T of n is 3n squared plus 4n plus 3. So my analytical is merely 3 star n plus 4 star n plus 3. And my empirical, I just list the statements and given a value of n and increment c on every one except for the return value. And as before, I have matching values for both the analytical function and the empirical function. Example 4 is I have two sequential loops, and so their analysis is pretty close to the same each deal. So when I get done, I have T of n is equal to 3a plus 3b plus 5. A is equal to n and b is equal to n, so T of n is 6n plus 5, and so my analytical function is return 6 star n plus 5. And my empirical function just takes the statements and increments c for every statement. And when I print out, why, they match out. So by this time, I'm getting quite confident that this technique of testing my analysis with empirical functions is valid and effective. Here I have a nested loop, but the sum runs to n squared. So in my line statement, what I note is that I have computed a value b for just one operation. But as I note here, while j less than n star n, that's really two operations, a less than and a multiplication. So really the cost here is 2b, but the number of iterations is b, so that when I get all done, I have T of n is 4b plus 4a plus 3. When all is said and done, T of n is 4n cubed plus 4n plus 3, which is what you would expect. We have a loop, the outer loop, that's the I loop, runs to n, so you would expect that would be order of n operations. And we have the inner loop runs to n squared, which we would expect to have n times n squared or n cubed operations. So we create a C++ function that computes n analytically, 4 star n star n star n plus 4 star n plus 3. And on our while loop that has a 2n instead of C++, we have C plus equal 2. And when we get ready to print these out, why, they too match exactly. For example 6, what I have is I have a nested loop where I runs from 0 to n to less than n, and j runs to I. So my I loop runs from 0 to n minus 1, but my j loop runs from 0 to I minus 1. So when I get ready to compute this, I compute b is equal to I equals 0 to n minus 1, j is equal to 0 to I minus 1. So that would be I minus 1 plus 1, so making a total of I times. And then I have from I equals 0 to n minus 1. So that would be 0 plus 1 plus 2 plus 3, all the way up to n minus 1. So we can use our arithmetic sequence formula, n minus 1 times n over 2, which is 1/2 n squared minus 1/2 n, arriving at a total of T of n is equal to 3/2 n squared plus 5/2 n plus 3. Now what we create is a C++ function that computes T of n analytically. And know what we're doing here. We're doing 3 times n plus 3 times n times n plus 5 times n. So we're taking the two values of n and adding them together. the two terms with n or n squared in them and adding them together and dividing by 2, so that we don't arbitrarily truncate this, because these are all integer values, and as we know, when we do division, we do a division by truncation. For the empirical one, we just code it as we listed it in increment c, and when we're all said and done, y, we find that our analytical and empirical values match exactly. Example 7, what we're doing here is we're dividing by 2 here. So as you recall before, we did the logarithmic, so t of n is going to be 4 floor of log 2n plus 2. So to do this, we create an integer function log 2 double x that returns the absolute value of x, so long as it's the absolute value is less than -4. The reason we're doing this is because the log of 0 is undefined. So what we're going to do is we're going to return this value only if it's a valid value. Let's see, int floor, and then the log to the base 2 is the decimal log divided by the log of 2.0. So what I do is I return the integer floor of log 2, and then I have to pass log 2 a double value, so I have to cast the n as 2. I have plus 2, and then I have just my regular empirical function, and what we see is that they match in every case.